If you have been always wanted to learn KiCad, this might be the right time to start. KiCad just released the new version, KiCad 7, and this is an introduction video for people who are just getting started with KiCad. If you are new to PCB, you can read the article we have published here, and if you are familiar with PCB, but this is the first time you are hearing about KiCad, here's a little pre-context. KiCad is an open source software for creating electronic schematics, printed circuit boards. Along with this, they also offer Gerber viewer, PCB calculator, 3D viewer, and integrated SPICE simulator. It's totally okay if you're not sure about any of the feature I talked about now. We'll make sure we discuss everything in detail throughout this KiCad series. So first let's start with downloading an installation of the KiCad. First go to kicad.org, then click on download. Now select your operating system. In my case it'll be Windows. Then click on the GitHub. Once you download that, I run the setup file. Now you can open the KiCad 7. So this is the project window which shows all the files that's related to the project. To have a better understanding, let's start with creating a simple project. You can either click on a file, then create a new project, or you can directly click on this icon to create a new project. And let me name this project as introduction. Now you can see two files have popped up. Here, the first file will open the PCB Layout editor, which helps in making the traces and arrangement of the components in a printed circuit board. Whereas the second file will open the schematic editor, which will help in building the circuit with electronic symbol that can be used for a reference. Now if you want to know where these files are physically saved to your system, you can click on this icon. That will take you to the folder where files are saved. Now let's quickly go through all the features that we have on KiCad as we open the project. First, we have the schematic editor. This is where we start our PCB journey by creating electrical connections between the components and how they work together. Then we have the symbol editor. KiCad comes with some standard symbols, but often there are situations where some symbols are not available by default. So KiCad gives an option to build and customize symbols by ourselves. The next we have is the PCB editor. This is where we take the electrical connection we did in the schematic editor and convert it into real-world PCB with proper measurements, the arrangement of the components, and how they are physically connected to each other. Followed by we have footprint editor. Just like the symbol, only some standard footprints are available in KiCad by default. In such cases, we can use footprint editor to make custom footprints. Before talking about the Gerber viewer, let me tell you what a Gerber is. Gerber is a final output file that we send it to a fabrication plant to manufacture a PCB from our design. So we can use this Gerber viewer to view the files before we send it to the manufacturer. Next, we have the image converter. This tool is used to convert image like JPG, PNG into the formats that KiCad can understand and place it onto the PCB. This process can be used to place logos, images, and other instructions onto the printed circuit boards. Next, we have the calculator tools. This tool can be used to color code the resistor, calculate the track width, the wire size, and electrical spacing, and plenty more calculations. Then we have drawing sheet editor. This tool will help in customizing the schematic editor sheet with names, logos, and other details which are very helpful in case you are sharing your designs online or within an organization. The next and the final tool that we have on the list is plugin and content manager. This will help in getting third-party features to KiCad which are made by community members, which we'll discuss more in the future. If you like to follow along, you can download the example project from the description. Once you download the project, you can go to File, Open Project, and you can open the User Interface project. Once the project is opened, open the schematic file. Now don't get overwhelmed with the amount of icons and tools on the schematic editor. Let's take baby steps and focus on a few tools at a time. This is the document where you draw your schematics and connections. Now if you like to zoom in and zoom out of the document, you can use the scroll wheel. And if you like to move across the document, you can either use the middle click and drag, or you can use right click and drag to pan across the document. Now if you look close to the taskbar, we have few values here. So starting with Z. So this Z indicates the zoom in and zoom out level. Then we have the X and Y coordinate of the cursor that we are moving around the screen. Followed by we have dx, dy and the distance. Now let me zoom into the schematic. Let's see how we can use the distance or how to measure distance between two different symbols. For example, if I want to know the distance between these two components, I can place the cursor on this component and press spacebar to reset the dx and dy value. And now we can move the cursor to the second component to see the distance. So this feature might not be very handy in the schematic editor, but it'll help a lot in the PCB editor. And now if I zoom in and zoom out, you can see small points where our cursor snaps onto. These are called grid points, which will be of great help when connecting two components together. So we don't have to fiddle around to connect them properly. And you can see the distance between them over here. And finally, the mm represents the millimeter. That means all the values that are shown here are in millimeters. There are a few more navigation tools on the top. You can see you can use these two buttons to undo and redo any changes that you make, followed by the find button to search for things on the schematics. And you can see once it finds the item, it's been highlighted by the pink color. Then we have find and replace, where we can use the find and replace to search for the text and replace them with a different text. Now let's say for some reason you're not able to use your scroll wheel to zoom in or zoom out. So that's the reason we have some additional tools on the top to zoom in and zoom out of the schematic editor, where you can use the plus symbol to zoom in and minus symbol to zoom out, and followed by the zoom to fit. This will try to fit your entire document to the display, just like this. Now if you want just your schematic to fit to the entire screen, you can use zoom to objects. So you can see your entire schematic is fit to the display. Now what if you want to zoom into specific component or a specific part of the circuit? For that we have zoom to selection. Click on this and we can make a selection which has to be zoomed in to fit the display. And that's how zoom to selection works. Now that completes a very minimum navigation that's needed in the schematic editor. Now let's dive a little deeper and start at the tools on the left and slowly work our way towards the tools on the right. This tool will help in turning on and turning off the grid, just in case if you want to take a screenshot or maybe you want to have a better look at the schematics. But I prefer keeping it on so I know where I'm placing my components and how they are connecting to each other. Now we have these three buttons which will help in setting the document units. You can either use inches, mils or mm. You can also see that's been reflected on the bottom. I prefer using mm, and all the dimension and calculation in the future videos will be based on mm. Next we have the crosshair. The plus graphic that follows around the cursor is the crosshair, and you can toggle between full screen and short crosshair using this button. And in most cases I use the short one, and in some cases where I need to align two components, in that case I switch to full screen crosshair. Followed by we have something called as hidden pins. This button will help in hide or unhide the hidden pins which are usually created by the power symbols. These three buttons will help in angle of the wire that's connecting between two components. I usually keep everything at 90 degree, but if you like to turn off and go crazy, you can do this. Or you can switch to the last mode to have an additional option of 45 degree. Now if you see the names D1, U1, U2, SW, they're called as designators, and it's auto-generated by KiCad. You can either keep this automatic annotation turned on so it creates the number for the new component automatically, or you can turn off and name all the components at the end together. I prefer the latter method where I turn off the automatic annotation, because if I delete something in between, I don't want to skip numbers. Then we have hierarchy navigator, which we'll discuss in the future videos as it's a tad bit complicated to understand for beginners. People who are just getting started might get overwhelmed by the amount of options and settings it has to offer. So learning each tool without real world examples would be very difficult. also a little boring. So in this video, this is the project that we are going to work with. It's a digital diya, which can react to light and also to sound and act almost like a real diya. If you are interested in this project, I'll drop a link in the description where you can find more information about this project. To start, I have created a new KiCad project and opened the schematic editor. From the previous video, you should be familiar with these editor tools and also how to navigate around KiCad schematic editor. First, let me show the circuit that we are going to build using the schematic editor. This is the complete circuit of the diya. If you're wondering how I build this, that will be a topic for another video. Here you can see I have one 80 tiny microcontroller, a few resistors and few other components. So we'll start with placing those components on the drawing sheet first. To get those components, you can either use the shortcut A or you can click on this button over here. This will bring up the components search menu and will search and add the components that we need. Personally, I love the way they have arranged all the components and how you can search for it. For example, if you need a resistor, all you have to do is just type R. And for a capacitor, you just have to type C. And similarly, for many basic and standard components, you just have to use one key search. For this particular circuit, we'll start with the resistor. So I'll start with R and click OK. Now you can see the symbol follows the cursor, and once you do a left click, the component is placed on the document. Hi, sorry for the interruption. Just a quick note, I might have forgotten to mention in the previous video. You can also look at the bottom status bar to know which tool you have currently selected, and you can use escape key to go back to the default selection. Since the currently selected tool is add symbol, click again and add another resistor. But before placing, what if I want the orientation to be different? In that case, I can use the letter R for rotation. This will rotate the symbol but won't be placed on the document until you do a left click. Now to go out of the tool, you can press the escape key. For my taste, the resistors look a little far from each other. What if I want to move them very close to each other? You can hover your cursor over the symbol and press M. Now you can move around the symbol as well as simultaneously you can change the orientation of the resistor by pressing the letter R to rotate. Once you are satisfied with the placement, you can just do a left click. Now let me quickly place all the remaining components on the document. You can see the 80 tiny 85 pinout looks a bit odd and doesn't match the standard convention for numbering from left to right. This is to optimize the symbol on the circuit diagram to make it look neat. Usually, the positive power symbol is placed on the top and the ground is placed at the bottom. And in some cases, they would also group few pins together for easier understanding. If you noticed, I haven't placed the symbols for the power and ground yet, because you can access this in multiple ways. You can either use the add symbol and search for the ground, or you can use the next button on the list, add power symbol, to search power symbols specifically. And for some reason, if you like to delete any of the components, you can just hover over them and press the delete key, or you can use the delete clicked items tool and click on the item that you want to delete. Now before connecting all these components together, there is one crucial thing that I'm missing. That's the value to the symbols. Currently they are just set with their default values R. We can change this value just by hovering over the symbol and by pressing the letter V. And here you can enter the value of the component. And if you look a little down, you have few more additional options to customize the way they look. But for now, I'll just keep them to default. Seems like only the single R value changed. What about the R and the question mark? These extra values are called designators and they are currently mentioned with question mark because I have turned off the automatic annotation. Once we complete the circuit, I'll show you how to automatically number everything together at once. Now we have all the components on the document, and if you like the placement, we can start with connecting the wires together. You can either click on the button below the power symbol, or you can use the shortcut W. This will bring up the wire tool. I can make the connection just by clicking on one pin and then clicking on the pin of the other symbol. If you like to control the way the wire is connected to your component, you can use the left click while moving to the next component. And if you remember from previous videos, we can use these tools to make varieties of connections. There are also ways you can change the appearances of these wires that connects the symbols. Now go back to the selection tool by pressing escape and hovering over the wire, press the letter E. So this should give you the width of the wire, also the color of the wire that you like to set. But personally, I like the default settings KiCad provides. So I'll just revert back to the previous color. Either you can use the undo button or by just pressing Ctrl Z. Now let me go quickly arrange these components and connect them all together. Let me be honest, this is one of the ugliest circuit I have ever done. It's just I wanted to use the same tools that I showed you in this video to make the entire circuit. And this should be good enough sometimes if you don't care about people looking at your circuit and you're just doing for your reference. But this is not good enough if you want to build a PCB or share this circuit to someone. But so far, it's a very good progress. Now let's concentrate back onto the circuit and let's try to make them look prettier. Just like the components, each connection has its own name. For example, the name of this connection is called ground and connection name for this is 3.3 volt. And similarly, different connections will have different connection names. This feature might look very simple, but this is one of the powerful features of KiCad. Even if the connection is not manually made, but the two components have the same net name, they will be connected in the backend by KiCad. This is great feature because we can avoid overlapping and have way too many connections going across the drawing sheet. But these names, ground and 3.3V, are automatically assigned by the power symbols. But this is not the same case for all the connection that we have done here. Let's look at this connection. So you can see it does not have any net name. In that case, we can create a custom net name for the connection. In the toolbar, select add net label and we can give a name for the connection. Let me call this LED and hit OK. Now we can add this over here. Now press escape to go back to the selection tool and click on the connection again. And now you can see the connection name has been updated to LED. Here you are free to choose whatever the name you need, but I would suggest keeping them meaningful, not just use some random letters and symbols. Now let me quickly do this for all the nets and try to avoid all this overlapping. It looks way better than before and also more readable. Now there are a few pins we don't use, like this pin number 3, 1 and 5. And these pins can be a little troublesome when we are doing electricals rule check, and also it doesn't clearly communicate what those pins do. So KiCad provides a no connection flag that we can use, which will make sure we don't connect any components accidentally to these pins. For that, go to the toolbar and click on the no connection flag. And now we can just click on the pins that we don't need any connections. Now along with this, we'll try to fix the values and the designators. From the previous video, you should be familiar with adding the values. And also in the previous video I told, once we finish the circuit, there is a way to automatically number all the designators. For this, go to the annotation tool on the top. Now make sure the entire schematic is selected, and also we'll reset any existing annotation. Once that's done, just click on annotate. Now if I close this, you can see all the values have been updated with their respective numbers. You can see R1, R2, R3 and R4. And similarly, we have MK1, D1, U1, BT1 and SW1. Since there are no more annoying crossover connections, we can create sections of this circuit which are way easier to understand. We can name this section using the text tool. So we'll add a text. Now I'm copying the text using Ctrl C and Ctrl V. And if you like to edit the text, just hover the mouse over the text and press the letter E. So this setup looks good, but it would be much better if I can clearly define the sections. So for that, we can use these tools to properly separate them into each individual units. So for now, I'll just use the rectangular tool. Just click here, add here. I'll press the letter E and change the appearance of the rectangle. And this is totally personal and I like to go with this style. And hit OK. Now let me quickly do that for the rest of the circuit. And if you compare this circuit with the previous one we built, you'll realize how readable and how pretty looking the whole circuit is. Now to make it much better, you can also add logos and other images if you wish. Let me show you how to do that. Go to your add bitmap image and let me add the logo. Add the image and resize the image. I'll just add this over here. If you need to share this circuit online and have a link to your website or to the project page, you can use this text box. And we'll create this. And this is a new feature, and previous version like KiCad 6 and KiCad 5 did not have this feature. Now this completes the feature of the schematic editor. It's always good to double check because there is usually a high possibility that we make some sort of mistake. So KiCad offers some basic checklist that would help us build a very robust circuit with very minimal error. You can see this checklist on the schematic setup. Now go to the toolbar and click on the schematic setup. Now under this, click on the electrical rules. And here you can see all the rules that KiCad has previously set up for us. For example, pin not connected, a pin with a no connection flag, and we have duplicate reference designators, and symbol is not annotated, and many more. This takes care of a lot of tiny details that we easily miss out on. I suggest not changing any of these settings unless you know what you're doing with it. Now let's see how to perform electrical rule check and see if our circuit passes all those rules. Go to the toolbar again and click on perform electrical rule check. And then click on run ERC. Here you can see we have 1 warning and 2 error. And you can use this checkbox to select what you want to see and what you want to ignore. In our case, first let's start with fixing the errors and later focus on the warning. So I'll just uncheck the warnings. Let's start with one error at a time. The first one, pin not connected. So in the previous video, I mentioned we need to place no connection flag on the pins that are not used. This is to tell KiCad that we are willingly giving up the pin and it's not an accident that we missed connecting those pins. So I'll click on add no connection flag and then add the flag to the pin. Now let's run the ERC again. And you can see the number of errors reduced to 2. And these 2 errors would be the most often errors that you can face on KiCad before moving on to the PCB editor. This basically means KiCad doesn't know which net carries the power and not sure how the components are powered. So this can be easily fixed. All you have to do is go to add power symbol and search for power flag. And now we just add this to VCC and ground. Once that's done, we'll run the ERC again. And you can see we have solved all the errors. Now we'll look at the warnings and see how to fix that. So the switch S1 has one unplaced unit. So what does this mean? To better understand, we'll try to add the same symbol again. So I'll go to add symbol and we'll search for the switch. You can see the switch contain two units, Unit A and Unit B. This is KiCad trying to simplify the double pole double throw switch into two single pole double throw switches, which is technically correct. And the circuit we have built still holds good. We can also go ahead with the warning and go to PCB development. Because this is just a symbol that represents the switch, it doesn't have any physical dimension or shape of the switch assigned to it. But I would prefer to fix the warning before we move further. So let's search for single pole double throw switch and replace it with the existing switch. Now when you try to do the electrical rules check, you can see the schematic is not annotated. So if you make any changes, make sure you annotate before you do the ERC again. So let me do the annotation. Then let's click on ERC and let's run the ERC again. And you can see we have zero violation and the circuit is perfect. There are a lot more errors and warnings that you can face while using ERC, but covering each one of them wouldn't be possible. But most of the errors are readable and self-explanatory. If you need any help, you can always reach out to us at PCBCUPID Q&A. So far, we have completed the schematic. This is perfect to share and showcase your circuit. But most of the components here on the circuits are generic. For example, we use the resistor R and its value. But we are unaware of the type of the resistor, either it's SMD or a through-hole component. And also we are not sure what is the wattage of the resistor. And for few of the other components, we might have a different brands which might have same functionality but totally different physical dimension and its appearance. To fix this, we have the footprint assignment tool in KiCad. This assigns each symbol with its physical counterpart called footprint. I think you get the idea why it's called footprint, because we considered the 2D cross section of the component and how it's placed. For analogy, we can consider a human footprint. Just by seeing the footprint, we can figure out how the person was standing and in some cases, what he was trying to do. Similarly, we can use the component's footprint to determine the orientation and the placement of the component. Since we nailed down the basics, let's see how we can do this in KiCad. You can open the footprint editor on the toolbar. You can see some of the components are assigned by KiCad and some of the unassigned components are highlighted in yellow. It's not possible to have all the components in the world within a single software. But KiCad does have a huge collection of footprints. In later videos, we'll discuss how we can make our custom symbol with a custom footprint. First, let me quickly walk you over this footprint assignment window. If you look at the left, we have all the component names, example, resistor, capacitor, diode, and LED. And now see on the right, we have the actual footprint for each of the component. To view the component, select the footprint and do a right click and click on View Selected Footprint. This will take us to a window which shows us the 2D cross section which I was talking earlier. Now if you want to know how this looks in 3D, you can either use this icon or press Alt 3 to see the 3D view of the component. In upcoming videos, we'll discuss more about this 3D viewer. Also, we'll discuss more about this footprint editor. For now, let's go back to the footprint assignment tool. There are few key points that we need to consider before placing the footprint. Can we source the component? Just because the footprint is available on KiCad, that doesn't mean we can get the physical component easily. Make sure to do the research for the parts and see if it's easier to source. Importantly, make sure it is available after a few months, also after a few years. Imagine if the design and the components aren't chosen properly, the PCB will become obsolete very soon and we might have to redesign the whole thing again. Is the component cost effective? Always check if the components are cost effective. The whole reason to build a PCB is to keep the cost down during production while doing higher quantities. So even a small difference for one PCB can make a huge difference while mass manufacturing. Cross-check with the datasheet of the component. Each component will have a datasheet and its footprint and its physical dimension. Just double check if your footprint is matching the dimensions. If you're just getting started, I highly recommend getting the components on hand and then assign the footprints. Don't do guesswork or don't rely on datasheet. because some of the vendors may provide a totally different data sheet and supply completely a different part. It takes time and experience to find a reliable vendor who can ship the promised product at low cost with fast delivery. Can machines assemble it? We can sometimes choose the low cost component or a part that works for the circuit, but it might come with a caveat of us assembling it manually. It should be totally fine if you are doing a few PCB or planning to do a smaller quantity, but this would increase the cost drastically during large production because manual labor is way more expensive than machines. These are just a few points and there's a lot more to consider as you scale up. So let's start from the menu bar. We have the footprint libraries. Here you can see all the footprints that are available on KiCad and also where it's physically stored on your computer. And this is where we also include external libraries and custom libraries that's created by the community members. Then we have view selected footprint. This will open the footprint and show it on a different window. You can either use this button or you can click on the component and then do a right click on view selected footprint. This is the footprint window. It's fairly easy to use and most of the tools and navigations are very similar to the schematic editor. You can zoom in and out and also pan just like how we do it in schematic editor. Also you can use these tools that we discussed in the schematic editor. There are only very few new tools like this measuring tool to measure the component length and components width. Then we have hide and unhide the pin numbers. Then we have the outline modes for the pads. Then outline mode for the text. Then finally we have outline mode for the graphics. This window is just to view the footprint. There is no way to edit or modify the footprint. In the future videos, we'll look into how to customize and edit the footprint using footprint editor. For now, let's continue with the footprint assignment tool. Now if you want to go through all the unassigned components, you can use these two buttons to navigate and find the unassigned components. I think you would already know what these two buttons are for. They just undo and redo the last edit we make. The next we have the automatic footprint assignment. This button is where I was fooled a little in the beginning. Initially when I saw this, I thought KiCad would assign all the components with some default footprints. But that's not the case. KiCad uses a special footprint association file to assign them automatically. We can find this under Preference, Manage Footprint Association File. And this is where we add the footprint association file. Let me give you a gist of how it works with an example. So I have a few collection of components. Based on this, I can create a footprint association file with the format that KiCad is looking for. Once that's done, I can include this footprint association file while doing any project, and it will automatically assign the footprints to the components that I already have. This will reduce a ton of work down the road, but this is definitely not something you need to use if you're just getting started. The next one is pretty simple. It'll just delete all the footprints that is assigned to the symbols. Now if you look at the bottom status bar, we have over 12k footprints. There are times when your PC gets slower as you search for a components. To solve this, KiCad has a custom filter that we can apply during the searches. For now, we'll try to select one symbol. So I'm going to choose the resistor R1. Now we can try to narrow down to one footprint for this resistor using these filters. First we have the filter footprint based on the symbol description. So if I select this, you can see this will just show us all the footprints that is related to the symbol. In this case, you can see all the components that are related to resistor. And we have brought down the footprint count from 12k to 177 footprints. To reduce this further, we have the pin number filter. For a fact, we know that our resistor have 2 pins, but some of the footprints here have more than 2 pins. For example, if you look at the resistor R_array_SIP4, you can see this footprint is made of 4 pins. So we'll remove the footprints that have more than 2 pins by selecting the pin filter. Using the information we gave, KiCad will narrow down the footprints to just 136 from 177. But it does show footprints from various libraries like SMD, THT, and also optical devices. In our case, we just need the through-hole component. We can do this by using the next filter, filter by library. Turn the filter on and just click on the footprint library where we need to search. That would be resistor THT for through-hole. And you can see we have narrowed down the component from 12K footprints to just 88 footprints. That's amazing. We are now just left with narrowing down to one footprint that we can assign. First, let me see what I have in my collection. I have the resistor with the length 6.3 mm and the diameter of 2.2 mm. Now, how do we find this footprint in KiCad? Let's break down the names that's available for us on KiCad. We have the package name, resistor THT, followed by a DIN code. This is a standard used to differentiate various types of resistors that's available in the market. Then we have L, which tells us the length. We have D, which tells us the diameter. Then finally, P stands for pitch, which tells us the distance between the leads. Also, we have the orientation, either vertically or horizontally. I would choose this footprint. And if I measure, we approximately have the length and the diameter a little above 2.5. And also I like to place the component horizontally. There are also a lot more reasons to choose a particular footprint. For example, a design constraint or a assembly constraint. But many of those you'll just learn with experience. Now before adding this footprint to the symbol, I just want to have a better picture in my mind. So we can use the 3D view button by clicking this icon. Don't worry about these tools and navigation, we'll have a dedicated video for this. But for now, just remember, right click and move to rotate the PCB, middle click and move to pan, and finally you can zoom in and zoom out by using the scroll wheel. Since now I know how the component is placed on the PCB, I'll just exit this and go to the footprint assignment window and select the component and then double click on the footprint that needs to be assigned to the symbol. Perfect. Let me quickly do this for all the resistor. I'm choosing the next component as LED. This should be exactly the same as the resistor. First, let's select all the footprints that have the symbol description. Then select all the footprints that have just 2 pins. And finally, let's use the LED THT library. Then based on the LED I have, I will choose this particular footprint. And I'll follow the same process for rest of the components. Now we are at the tricky part. We don't have a footprint for the condenser microphone in KiCad. In this case, I would usually either download a custom footprint or make my own footprint using a footprint editor. Since we never discussed to that point yet, we'll try to find another symbol with similar shape and dimension and replace it for now. After a few minutes of searching, I figured out this is the best alternative we have. So this has the same pitch distance between 2 pins similar to the condenser microphone that I have. But this might cause some issues with the other dimensions of the condenser microphone. For example, its diameter. But we can fix that while making the PCB layout. Since we have successfully assigned all the footprints to the symbol, we can just apply save schematic and continue. Once that's done, you can click OK. Now you don't have to follow me, I just want to show in 3D how all the components look together on a PCB. In the next video, we'll see how to use the PCB Layout editor and arrange the components, followed by routing all the components. Let's quickly discuss what PCB is composed of and how we can relate them in KiCad while using the PCB editor. Printed circuit boards are made of various layers stacked up. To keep things simple, let's talk about single layer PCB. First, we have the base. It's a fiberglass material which is solid core that gives the PCB its rigidity and thickness. It mechanically holds the connection and the components just like the perf board or like a breadboard. Then we have the conducting layer. In most cases, this conducting layer is made of copper and connects the electrical connection between the components just like the traditional wires. These connections are called traces and it can be of various width and length depending on what we are planning to connect, which we'll discuss in more detail as we make our own PCB. Also, every time I talk about layers in PCB, like a single layer, double layer or a multi-layer PCB, it generally refers to the amount of conduction layers in the PCB. We can actually stop the production at this stage, just having the base layer and the conduction layer. Let me show you an example. You can see this PCB is almost usable and it does its function. But if you have noticed in day-to-day life, our PCBs are not like this. It's a little different. They come in a green layer on top of this, and that's called solder mask. It protects the PCB surface and insulates the copper circuit from oxidation. It also prevents accidental contact with other materials, solder, or any other conductive bits. It can be of any color, but it's mostly green because it's easy on eyes, and also it's easy to see the difference between different traces, planes, and empty spaces. However, the solder mask doesn't cover up everything on the board. It's applied in such a way that it covers up the small traces, empty spaces, but expose some space around the component pad so they can be soldered later. Finally, we have the silk layer. This is the layer at topmost with the names, letters, symbols, and usually white in color. It makes the assembly and final working of the PCB way more convenient. And it does not add any physical or electrical feature to the PCB. It is just for appearance. Sorry for going a little off topic over there, but trust me, this will help a lot in understanding while building the PCB on KiCad. Now let's quickly look at the PCB layout editor. For that, you can either click on this schematics.kicad_PCB, or you can open your schematics and click on Open PCB in Board Editor. So this will open up the empty PCB layout editor. And it's pretty simple to use. It uses the similar buttons and navigation style from the schematic editor that we learned. Since we already know the basics, we can directly start with the PCB Stackup that we discussed a while back. So let's start with setting up the board. Click on this board setup icon. And under this, select board Stackup. You can see it automatically selected board editor layers. And here, the prefix F stands for front and the prefix B stands for back. So basically it's the front and back side of the printed circuit board. Based on these prefixes, we have several layers that are used in a PCB. But you can see we have quite a lot of PCB layers than what we discussed previously. So let's try to cut down the things that's not necessary and also discuss few things that we didn't discuss before. First, we have the F.courtyard and B.courtyard. This layer defines a safe area around a component, so while assembling a physical component, they don't overlap each other. And you can see this has been marked with a pink outline. Then we have F.fab and B.fab. Using these two layers, we can give more data to manufacturing without including them in our final design, like mentioning some important points or notes. We won't be using both of these layers, so we can turn it off for now. Then we have F-adhesive and B-adhesive. This layer would be required only if your component is not easy to mount and require any additional glue or additional material that has to be included. So this layer would indicate where the glue should be applied and where it shouldn't be. In our case, we won't be using that feature as well. So we'll be turning off the B-adhesive and F-adhesive. Now followed by that, we have F-paste and B-paste. This two layer would have the information about where we shouldn't apply the solder mask so we can solder the components. Also, these layers are essential in making stencils, so sometimes these layers are also called as stencil layers, which we'll discuss in the future video. Now from the beginning of the video, you should be familiar with other layers, F-silk layer, F-mask, and FCU stands for conduction layer or copper layer. Similarly, we have the back copper layer, we have the back mask, back silk layer. So since we are familiar with this, we can just move forward and see edge cut. This layer would define the PCB shape and its dimension. And we can use the margin layer to define the area where the components, traces, and any other parts of the PCBs are allowed to be placed or not allowed to be placed. And there are a lot more layers that we won't be using, so we can turn off the user echo. This layer used only if you are sharing the PCB layout file to other engineers, where you can include the revision number of the PCB or any other graphics, drawings, which won't make into the final PCB. We can also turn off the drawing and comments, which are generally used for user reference and nothing much to do with the PCB. Finally, we can also turn off all the user layers. They are user-defined layers where we can add special features to the PCB and also to convey some information to the fabrication plant or to some other design engineer. Now just click on OK button and you can see Only the required PCB layers are visible and the non-required ones are ignored. Now we can go back to the board settings and now let's click on physical stackup. If you're just getting started, you don't have to worry most of this. Most of these features are taken care by the manufacturer. All you have to do is just select the number of layers that we are going to be working on. For now, I'll just select 2. Then next we have the board finish. This gives us various options to have a surface finish for our PCB. I'll make sure to drop a link in the description which will take you to this article where we have written everything in detail about each type of surface finish. Then we have the solder mask / paste. We can use the information provided in the manufacturer website and fill this information. But most of the cases, you could have pretty good results with just default values. So I'll just leave it as it is for now. Next we have the text and graphics. These settings are just for appearances and it doesn't affect the PCB in any way. We can change the line thickness, text and other informations. In the next video, we'll add some design rules and bring all the footprint into the PCB layout editor and start with laying out the PCB. For this, we'll go to the board setup and then click on constraints. Here we need to fill in the values that a fabrication plant can handle. So anytime we go above this threshold value, KiCad will warn us and try to keep our design within the manufacturing limit. Usually all fabrication plant will provide a capability list which we can use to fill in this data. If you're just getting started and not sure which fabrication plant to choose, we have a whole section of articles dedicated to that. For now, I'll use this capability list because most of the manufacturers can handle these values very easily. In KiCad, we have these default constraints. Let me quickly explain what and why we have these constraints using some examples. First, we have the minimum clearance. This would be the minimum distance between 2 tracks. And when we go below this value, we might see some weird artifacts or shorting of the tracks. This is because of the process called etching, which is done during the production. To avoid this, we can always design the board a little above the fabrication's capable value to be on the safer side. So in this case, the capable value is 0.1 mm. But 0.15 is a good value and also is recommended by the fabrication plant. So we'll go with that. Then we have the minimum track width, which is basically the thickness of the track. And similar to the previous value, this thickness is greatly affected by the etching process. If it's anything below the threshold value, the tracks might cause open circuits in the PCB. And according to the capabilities list, it is 0.15 mm. Then we have minimum connection width, which is similar to the track width, but this is the connection between two components or connection between a component and a track. Similar to the track width, if it's less than the threshold value, the PCB etching process might break the connection. So we'll enter the similar value. Then we have the minimum hole size. In this case, it's 0.3 mm. You can go well below this value, but it would make the PCB very expensive as they have to use different process to make the hole instead of just using a drill bit. Next we have the via size of 0.5 mm and the annular clearance is 0.1 mm. Sorry for throwing random words at you, but the video would get longer and longer if I explained each one of them. To solve this, we have created a cheat sheet of all the terminologies into a single page, which you can always refer to when you don't understand these terminologies. So I entered those values over here, 0.3, 0.5 and 0.1 mm. Finally, we have two more clearance values, minimum track distance and minimum track distance between the edge of the PCB. The first value will help in making sure we don't take the tracks too close to the holes, so the tracks won't be damaged while drilling during production. Similarly, the second value will help in making sure we don't take the tracks too close to the edge of the board, so it won't be damaged or chipped off during the final stage of production. The hole-to-hole clearance just makes sense. You can't have two holes close to each other during drilling, so they don't form a single slot instead of two different holes. Then we have micro vias. These are way little too advanced for the current circuit that we are working on. So we'll just skip this and go to the silk screen. Here, most of the terminologies are self-explanatory. So I'll just take the values from the capability list and just enter them over there. We'll come back to these values when we are doing zone filling at the end of PCB design. Then we have length tuning, which we can just keep it checked. Next, we have predefined sizes. Let's predefine some track width which we can use in the circuits. It's very similar to how we choose a wire to make the connection based on the current rating of the circuit. For this circuit we are working, we'll just need two different sizes, one for signals and the other one for power tracks. To calculate this, we can use the calculator that's within KiCad. Just go to the KiCad's project window and click on Calculator Tools. Then click on Track Width. If you like to know how the calculation is done, you can see the formula is given here with some explanation. Since our circuit is very simple, we can just enter the maximum current it would carry during operation. I'll just enter 1 amp for now. I know the circuit we built in the previous videos won't even be close to 0.5 amps, but decreasing the current consumption decreases the track width, which will make the track width less than our clearance value that we just set a while ago. Then for the temperature rise and trace length, I'll just let them be default. As the circuit is simple and small, these factors won't affect much. Then finally, there is one more factor to include, that is the trace thickness. And for this value, we have to pull up the capability list again. And if you look at outer layer copper thickness, we have 35 micrometer, 70 micrometer and 105 micrometer. In our case, we'll just go with 35 micrometer, which is also the default setting on KiCad. Now based on the information we gave KiCad, it gives the track width of 0.3 mm, which will include in the predefined sizes. There is also something called as internal layer traces. These values we can consider when we are trying to build a multi-layer PCB. So this won't be much of help now. Since now we know the track width, I'll create a 0.3 mm track width for signal, and additionally I'll create a 0.5 mm track width for power. I'm doing this just to show the difference between power and signal tracks. But theoretically 0.3 mm would be good for signal and power in our circuit. Then we have net classes. If you remember from our fourth video about schematics and adding net labels, we discussed how we can give name to few connections for easier understanding. Similarly, we can use net classes and create a group of connections that will share similar properties. For example, we can create two net classes, one for signal and the other for power. Now using these two classes, we can assign the thickness to the traces automatically. Instead of using the predefined sizes, each time we switch between power and signal tracks. So far we have just created the classes, but never really assigned the classes to the connections that we made in the schematics. We can do this in two ways. We can either do the assignment here on both setup, or we can do the same on the schematic setup. Personally, I would prefer using the schematic setup. So let me close this. So let me open the schematic editor. Now if you click on any connection and see the bottom status bar, you can see we have the connection name, but the net class is set to default. But in our case, we want to change this to signal. We can do this in multiple ways, but the easiest way would be just do a right click on the connection and click on assign net class, and under this the current name is set to /LDR. This is just the net label that we assigned, and here we can set what kind of net class we need to assign for this connection. In this case, we'll set it to signal and click on OK. Now if I click on the same connection again, you can see the net class is set to signal. Now if I click on any connections that's related to LDR, you can see the net class is automatically set to signal. We can either do this process for all the connections, or we can go to the schematic setup, and here we can just enter the name of the connection, and KiCad will try to automatically assign the net classes for these labels. So let me do that for mic and set it to signal, and similarly let me do it for LED and signal. Then we have ground, that will be the power. Then we have plus 3.3V, that will be power as well. Now there is a slight bit of a problem here. We have assigned the net classes only to the connections that have names. But what about the ones that's unlabeled? For example, this connection which has the default connection name net D1K and net class is default. Since they are unlabeled, there is no way to search for the pattern without a name that we manually assigned. So how about we manually try to assign? Seems like we can't assign the net to this connection without adding a net label. We can fix this quickly by adding a net label. But this process would become very difficult when we are trying to make a complicated circuit. In KiCad 7, we can solve this by using Netclass derivative tool to assign netclasses to unlabeled connections. Click on the icon here, add a netclass derivative label. On this menu, select the netclass that we want to assign to the connection. In our case, it's the signal. We can use the below settings to show how they appear on the schematic diagram. In my case, I'll keep it very simple, select the dot, and also I'll cut down the length by half. And then hit OK. And now we'll place it on the connections. And personally, I don't like the names that's sticking out, so I'll click the netclass label and press the letter E. And under here, you have the option called Show. And I'll just uncheck this and click on OK. Now with this, when we click back on the connection, we can see on the status bar that the net class has been assigned to this connection. Now I explained how to assign the class name for labeled and unlabeled connections. Let me quickly do that for the whole circuit. Now I have assigned all the net classes. To just make sure the schematic editor is reflecting all the changes to the PCB editor, I'll close this and open the PCB Layout editor. And here I'll open the board setup. And here we can verify both setup net classes and the schematic setup net classes match up. I know this is an insane amount of work for a very simple circuit, but you need to trust the process. These settings will really help a lot in making a very good PCB at the first try. I've already shown what we are going to build in the beginning of this series, so most of the features and the mechanical design is already done. In this video, we'll just take the design for the reference and we'll figure out where to place the components around the PCB. When I said we'll refer to the 3D model, I don't mean that we'll use the exact dimensions and try to make a PCB. Instead, we'll just start with all the basics of PCB Layout editor, and in the upcoming videos, we'll optimize the PCB so that it can fit inside the 3D model. But for now, let's start with defining the shape of the PCB within KiCad. If you remember correctly from the PCB Stackup video, we can do this in the edge cut layer. So make sure you select the edge cut layer and then click on the circle tool. Now we'll draw a circle on the document of any radius. Now to open the properties for this circle, there are three different ways. Either you can use the property manager over here, or you can hover your mouse over the circle and right click, then click on properties. Or the one I always recommend is use the keyboard shortcut letter E. By using these properties, we can change the location of the circle on the document. And by using these properties, we can change how the circle looks on the document. For now, let's just stick to radius, and I'll change the radius to 30 mm. And along with this, I make sure I selected the lock property. This will make sure we don't move the circle accidentally or resize them. And you can see once the property is applied, I don't have access to the circle anymore and I won't be able to select it. But if you want to apply some changes to this shape, we can do that by going to the bottom right corner and under selection filter, click on locked items. Now we can select the circle again and edit the properties. This selection filter will help in selecting only the required items and it will prevent users from selecting unwanted feature of the PCB. In this case, I'll make sure to turn off the locked selection. It's not mandatory, but this will prevent me from accidentally changing the locked values. Now going back to the PCB, we can quickly verify that we have defined the shape of the PCB on the 3D viewer by using the shortcut Alt+3. This will be the output of the 3D viewer. And the output will be similar only if the shape is on the edge cut layer. If the shape is drawn on another layer, KiCad will try to automatically draw the edge cut layer based on the content we put on the document. Since we have the base ready, all we need to do is get the components and place it within this circle. It should be pretty easy as we converted all our symbols into footprints in one of our previous video. On the top toolbar, click on the Update PCB button. This menu will help in importing all the symbols with footprints into the PCB editor. Here, just make sure all the three options are checked. And if you like to know what each one of them does, you can just hover the cursor over them. And they'll show pretty good explanation about the options. Now with these settings, I'll just click on Update PCB and then hit close. We can see the complete circuit is imported and moves along with the cursor. I'll just bring the cursor close to the circle and try to place within it. The circuit is little chaotic now and not properly arranged. We need to arrange this component in such a way that it's easy to fit on the 3D design I have already done. For reference, you can download the 3D model from the link in the description. I hope you're already familiar with most of the tools on the editor. They are very similar to the schematic editor tools that we learned. So here I won't go into much detail how things work. So according to the design, it would be better if I place the cell holder on the back and place the microphone at the edge of the PCB, as it would be the first thing to be mounted on the 3D model. Then we'll follow it with a LDR. Then finally the LED. We won't have much control over placement of these components because of the design choices that's made to implement the features. But we can move the other parts around and optimize the space occupied on the PCB. I hope you observe these thin lines going across the components. These are called rat lines. They correspond to how the components are connected in the schematic diagram. If it's annoying, we can turn it off by toggling this button. And if you're not a fan of straight lines, you can also toggle this button to change the way the rat lines are drawn. Sometimes these lines can be very confusing if you have way too many components. In that case, we can turn off all the rat lines and use this tool. This tool will draw rat lines only to the footprints that are selected, and you can remove them by clicking on the footprint again. But for now, the rat line informations are very much needed, so I'll bring them back. We can use the rat line information and place the components close to each other based on the connection. Overall, this looks pretty average, but if you have OCD like me, I hate how these components are not aligned. We can quickly fix this by selecting these resistors and then right click, go to align, and then we'll align it to left. I'll do the same thing again, go to align, but this time I'll select distribute and click on distribute vertically. And you can see we have even space between these components. Now using this feature, I'll align all the components around the PCB. Now the circuit looks a little bit better. Now we can quickly check how this appears on a real PCB by using the 3D viewer. So I'll just use the shortcut Alt+3. This somewhat looks good, but it looks very odd with the pin for mic and no 3D model for few of the components. So let me quickly show how to add external 3D model to the PCB layout editor. Go to GrabCAD and we'll search for the component. Seems like we have one suitable option. And I think we found the model. And we can just go to the downloads and you'll find a different file format. Make sure you download .stp or .step file. Click here and hit on download. Now going back to KiCad, select the footprint where we want to assign the 3D model. Then right click, click on properties. Now on the top, click on 3D model and you can see the existing 3D model is missing. So we can just delete this. Click on the plus icon, then click on the folder icon. Then select the file that we just downloaded. You can see the 3D model does not match the footprint. It's pretty easy to match it up using the tools on the left. First, I'll reduce the opacity a little and then use the offset to move the 3D model on the x-axis. And I'll just turn the model and try to align the pins to the footprint. Once that's done, I'll bring the opacity back and then hit OK. Now when we go back to the 3D viewer, you can see the 3D model has been imported within KiCad. Now I'll quickly do the same for the switch. Now the circuit looks way better. In the next video, we'll see how to make the connection between each one of these components and also try to make the whole circuit look a little prettier. Let's make sure all the constraint setup and the net class assignment we did in the past videos are intact. So let me go to the board setup and then click on constraints. It seems like all the values are similar to what we set. Now to confirm the net class assignment, we'll exit this window, go to the appearance panel, and under that click on Nets tab. Here you can see all the net names that we assigned, and below we have all the net classes that we assigned. To confirm if the net classes has been assigned to the nets, we can turn off all the nets that's assigned to the power class by using this eye icon. So I'll just click on this. You can see all the nets that's assigned to the power class is been hidden. And similarly we can do to the signal class as well. You can see all the connections are hidden now. That's a pretty good sign, which says we have assigned classes to all the nets. But in case if you see any connection after hiding the classes, that means those nets are not assigned to any of these two classes. So make sure to watch the net class video and assign them to the respective classes. For now, let's unhide both of them and start with routing. Routing might sound like a complicated word, but in reality, it's just a process of connecting the footprints together using copper traces. It's pretty simple to do in KiCad because we already know how things are connected with the rat lines. Now to form the copper traces, we can use the tool that's provided by KiCad. It's called Route Tracks. Now I'll select this tool. Just select the pad and do a left click. We can see the trace follows the cursor, and also it gives us the option to end at 3 different paths. It's always recommended to choose the shortest distance. We can also do a left click while moving the track, which will lock in the position and give us more flexibility in using the track tool. If you have noticed, KiCad will automatically try to keep the connection at 45 degrees and also try to keep the distance short. You'll hear about these design rules a lot while working on a PCB, because minimum distance will reduce any unwanted inductance introduced by the tracks. And also avoiding sharp angles will reduce the effect called reflection. Initially when PCBs were invented, all the tracks were curved and you cannot see any sharp angles in the tracks. Because in early days the routing process was done by hand. But when the designers started using the early CAD software, it changed a lot. The early CAD softwares had a lot of difficulty in handling many curves, so they switched to 45-degree angled tracks. But I'm really not sure why it stuck around, even if modern softwares can easily handle the curves. Because even the 45-degree angle would cause reflection, but still way better than 90-degree. For optimal connection, it's always good to use a curve. In KiCad, we can do this by selecting the tracks, then do a right click, then click on Fillet, then we'll enter the curvature radius of 5 mm and then hit OK. Here you can see we are using curves to connect these two paths instead of using an angled track. I'll give a link in the description where you can learn more about these reflections and why we need to follow these rules, and also why do we need optimal angle for the traces. Anyway, now with the basic rules of no sharp angles and keeping the track distance short, I'll quickly try to route most of the footprints. Here we can notice two different things. First, we have the different track width for different traces. That's because of the way that we assigned the net classes. So if I quickly go to the board setup, and if you go under net classes, the nets that are assigned to the power classes will have the track width of 0.5 mm, and the nets that are assigned to the signal classes will have the track width of 0.3 mm. And here on the top, if you see, we have the track and use net width class. So that's the reason we had the seamless switching between the different track width. But in some cases, if you want to force the track width, we can always do that. We can go under this drop down and select 0.3 mm. Make sure you turn this off so that we can use this particular width instead of using the width that is previously assigned to this particular pad. So since this is turned off and we have set it to 0.3, and when we try to do the track, you can see the track width has been changed. Anyway, now let's turn this back on and we'll use the net class width instead of us manually selecting them. So that's one observation. And second, you can see I haven't connected few of the connections. So this is just to show how we can switch between layers. Currently we are on the front copper layer And we can confirm this by going to the 3D view, and you can see all the tracks are on the top layer of the PCB and there's nothing on the bottom. Now to draw the tracks on the bottom layer, we can simply select the bottom layer and then use the same tool and start drawing. We can see I have connected the pads of the LED to the microcontroller through the bottom layer. Let's go to the 3D viewer again, and you can see on the bottom layer we have the LED track. So let me create a hypothetical situation where it's difficult to do on both top layer as well as on the bottom layer. Let me create a track over here. And if I go to the front copper layer, you can see I can just pass the bottom layer but not the front layer. And similarly, when I'm on the bottom layer, you can see I can't pass through this particular track. In this case, we can use one of the PCB feature called vias. Vias basically helps in making the connection from the top layer to the bottom layer. So we can use this to jump between layers. Let me quickly show an example how that's done. First, I'll go to the top copper layer and draw a track. Once I cross the bottom track, I'll just do a double click and then escape. Now I'll select the wire tool and then click on this particular track. Now let's go back to the bottom layer and continue drawing my connection. You can see I've made the connection between these two ground pads while using the track on both the top and the bottom layer. Now let me show how this looks on the 3D viewer. And here you can see the ground that's traveling up to here, and then the connection goes to the bottom here and it continues till here. So this is the reason why we use vias, to make a connection from the top layer to the bottom layer. Currently we don't have a much complicated circuit to show it, but vias will be of great help when you're working with SMD components. But in case of through hole, it's much easier to just use the pads as vias. But in our case, in this circuit, vias are not necessary. So I'll just simplify it by removing the via and connecting the track back to its original location. This PCB looks good, but will cause a lot of issues in terms of manufacturing, because we need to remove a lot of copper in the etching process to make these tracks, during which there are high chances that these tracks can become open circuit or short circuit within the PCB. To avoid this, we can add the copper fill. We can do that in KiCad by using this tool and then click on the document, and this window will pop up. And here in this window, we need to tell KiCad in which layers we need to do the copper fill. In this case, I'll make sure it is done on both the front copper layer and the bottom copper layer. And then we need to assign a net to this copper fill. It's not mandatory to connect a net to the copper fill, but you can see KiCad throws a warning telling that it will result in an isolated copper island. In this case, what people usually do is connect the copper fill to ground. We'll just select ground, and we can keep the rest of the settings to default and click OK. Now you can see a polygon tool follows the cursor. Now we'll use this tool and draw a boundary across the PCB. This copper fields that we created will not only help in the process of etching, but also will help in dissipation of heat from the components and spread them evenly across the PCB. We can go to the 3D viewer and see how efficient our PCB is now. You can see during etching process, the amount of copper removed from the PCB will be very small. This completes the PCB routing. If you remember from one of our previous videos, we performed ERC to check for errors and mistakes in schematics with the help of KiCad's predefined rules. Similarly, here in the layout editor, there are certain set of predefined rules along with the custom constraints that we set. Using this, we can perform DRC, design rule check, to see if our board design is within this set of rules. Now let's see how to perform DRC within PCB Layout Editor. Go to the top toolbar and click on Design Rule Checker. For now, we'll keep all the settings to its default and just click on Run DRC. Seems like we have no errors, but 3 warnings. Just for the sake of the video, I'll introduce few errors so I can show you how to fix them. So now let's run the DRC again. Now you can see we have 14 warnings and 4 errors. For now, we'll just focus on errors and we'll come back to warnings later on. So I'll just uncheck the warnings. The first error we have, courtyards overlap. Let's click on the error and see where it takes us. Here we can see the courtyard of two components overlapping each other. But how will this affect the PCB? So let's quickly see the same layout in the 3D viewer. On 3D view, we'll have a better understanding of what's happening. And if you carefully observe here, these two components are overlapping each other. This could cause some serious assembly issues if this particular PCB is sent for manufacturing. So always make sure you perform DRC before you send the files to manufacturing. Luckily, these are easy errors to fix. All you have to do is just make sure we have proper clearance between the components. Also try to keep the components without overlapping each other's courtyard. Now let's run the DRC again. You can see the previous error is gone, but we still have two more errors to solve. To see the other two errors, click on the Unconnected Items tab. This tab will show all the unconnected nets between the components. Since our circuit was very simple, I had to manually delete a few connections to force this error. But if you are working on a complex circuit with hundreds of connections, this particular DRC check will come very handy to find the missing connection. Now to see where the net is unconnected, just click on the error. It will take us to the location where the nets are unconnected on the PCB layout. And here you can see the arrows are making it very obvious that these two connections are unconnected. So I'll quickly use the route tool and make the connection between these 2 points. Now if I run the DRC again, we can see the previous error was solved. To find the next unconnected net, I'll just click on the connection again. And I'll quickly do this connection using the route tool. Now if I run the DRC again, you can see all the errors are resolved. Similarly, we can try to resolve all the warnings. So I'll check the warnings again and go to violations. We have 3 warnings, but it's less likely to affect the functionality of the PCB. So in some cases, it's okay to ignore these warnings and send the file for manufacturing. But it's always good to clear up all the warnings because these warnings can quickly turn up into errors when you work on the same PCB to improve the circuit or work on updating the features. Currently, the first 2 warnings are just telling us that KiCad cannot find the footprints that we are using from footprint library. But we know that that's not the case because we did use all the default footprints given by KiCad. These warnings can occur when KiCad's library is not in sync with the footprint used on the PCB editor. We can quickly fix this by right-clicking on the footprint and click on Update Footprint. And on this window, make sure Update Selected Footprint and then click on Update. And now if I close this and run the DRC again, you can see the number of warnings has decreased to 2. Now the next warning is very similar to the first one. So I'll just click on that, then select the footprint, right click and click on Update Footprint. And here I'm making sure Update Selected Footprint is selected and then hit on Update. Now once you go to the 3D viewer, you can see the cell holder and the switch is gone. That's because while updating the footprint, we lost the reference to the 3D model's location. But adding them back again will cause the same warning. Since anyway we are at the end of the PCB development and we won't be needing these references anymore, we can just turn off the 3D model and work with the PCB. Finally, we have one warning left. This warning is because of the constraint we set on the board setup using the manufacturing capability limit, according to which the silkscreen item should have a clearance of 0.15 mm. But if I click on the warning, we can clearly see that's not the case. So I'll just move this slightly away from the footprint and then run the DRC again. You can see we have cleared up all the errors and warnings. Now the PCB design is perfect for manufacturing, and also it follows all the constraints that the fabrication plant needs. Personally, I do miss having graphics and branding elements on the PCB. So I'll show you how we can add a logo or custom graphics to the PCB. Go to the KiCad's project window, then click on Image Converter. This window will help us convert the logo or image into a footprint that can be placed on the printed circuit board. To load up the graphics to the image converter, click on Load Source Image. And here, select the logo that you want to source. Here the current size of the logo is 158 mm. which is way too large to fit within our PCB. In this case, we can reduce the size of the logo to a lower value that can fit within the PCB. I'll just enter 5 mm. Now in this particular tab, it feels like there's nothing happening. To see the output, go to black and white picture tab. Since we have only one color on the silk layer, KiCad will convert the image to black and white, and we can adjust the output using this slider. In this output, the black part of the image will be applied with silk screen and the white part will be ignored. And if you like to invert it, you can just click on this negative checkbox. In our case, I'll just keep it to positive. So I'll just uncheck the negative and adjust the slider. And next, go to board layer for outline. Select front silk screen. Go to the output format and click on footprint. Now we can move this customized image to the board editor in two ways. Either we can save the image using export to file and use the image in all other projects, or we can just copy the image to clipboard and paste it on the PCB editor. I'll go with the second option. Copy the image using export to clipboard and go to the PCB editor, and before pressing Ctrl V or paste, make sure you select the front silk screen and then hit Ctrl V and select the location where you want to place the logo and then just do a left click. Now you can see there is excess text along with the logo. We can easily get rid of this. Just select the logo and click the letter E. Now under the reference designator, uncheck the show option. Then hit OK. Now let me try to add a text along with this. So I'll use the text tool and enter a text. Also, I'll slightly change the appearance to my personal preference. This looks pretty good now. We can add more graphics using the different tools that's available on KiCad. Let me show an example using the rectangle tool. I'll select the rectangle tool and making sure I'm on the front silk screen layer. Then draw a rectangle around the logo. So far we were working on the front silk layer, but we have a lot of empty space on the bottom that we can fill up with details about the PCB or more information that we like to add. I'll just go back to the PCB editor. Make sure back silk screen is selected. Let's add some open source and precautionary logos. So those are already inbuilt within KiCad. So we can just go to the add footprint tool. And under this, you can see various logo. For this example, I'll use designed with KiCad. Select this and place over here. You can see the footprint was placed automatically to the front silk screen, even though the option was selected to the bottom. In this case, we can just select the logo and then just do a right click and click on change side or flip. And now if you go back to the back silk screen, and you can see the logo has been placed on the back of the PCB. That looks pretty good. So let me add few more logos. This circuit is pretty much ready for manufacturing. We can't just send the KiCad file to the fabrication plant. This not only makes the process a little difficult for the manufacturers to convert these files, but also if this was a private design, you'll be giving up your intellectual property, where people can use the project file to edit the project, and also they'll have all the information about the circuit. There are hundreds, if not thousands of different designers and companies that use various different ECAD software. It's very hard for manufacturers to be expert at each one of them and use the data from the project file for manufacturing. So most of the final design file is converted into a Gerber file. So what's a Gerber file? A Gerber file is a collection of different files containing design information and vector coordinates of copper traces, vias, pads, solder mask, and silk layers. The best part about the Gerber file is it's human readable, and the Gerber file standard is widely accepted by all the fabrication plants around the world. So all the ECAD softwares allows exporting the design file into a Gerber file. This results in same output, which is independent of what software was used for PCB design. I'll make sure to drop a link in the description which will walk you through more in detail about Gerber and Gerber standard, which would help a lot in understanding why we use Gerber format. Now let's jump back to KiCad and see how we can export a Gerber file from our PCB layout editor. Now on the top toolbar, click on Plot. On this window, make sure the Gerber is selected and all these layers are included. In this case, I'm not going to include the margins and courtyard layers because we use these layers to keep our designs clean and help during DRC. Since we are past that stage, we won't be needing these anymore. Once that's done, now we have to set the location where our Gerber files will be generated. Here you can see I've already selected an output directory which is called Gerber. So you can do this by going to this folder icon and click on it and navigate to a location where you want to generate the Gerber file and then click on select folder. Now with this default values, we can just click on plot, but let's walk through a few of these settings and let's see why they exist. First, we have plot drawing sheet. This will include the drawing sheet data while generating the Gerber file, which will have the details that we have given to the drawing sheet like the name of the company and the project name. Let's keep this unchecked as it's not much of any use for manufacturers to see these details. Then we have plot footprint values. This will include the value of the components that are by default stored in the fab layer. But if you remember, we disabled this layer to reduce the complexity of our project. So just make sure to keep this option unchecked. Next we have plot reference designators. Unlike the footprint values, we do need the designator values, which is on the front sill screen. With this designator, we'll get a reference during assembly where and how to place the components. Next we have force plotting of invisible values and references. This option will force values and reference to be generated forcefully. Currently we don't have any invisible values in our project, but I would still recommend not using it anyway. This grayed out option will only work on few plot formats, but it's nothing we need to bother until we start manufacturing our own PCB. So let's just stick to the Gerber format. We don't have to use this option as well because it's on the fabrication layer which we disabled previously, but make sure to keep the next option checked, because KiCad will perform zone filling again before generating the Gerber file. So if we have messed up something while performing DRC, that can be fixed here. On the right, we have the drill settings. I'll just leave this and the Gerber options to default as they are already set with recommended settings. But if you like to learn more about these settings, you can just hover over them for more detailed explanation. Now with this setup, just click on plot. So you can see we got the output message done. So that means all the files are generated. So if I open up the output folder, we have the generator Gerber files which have various data about our PCB layers. But it does not contain any drill information like where and how the holes have to be drilled. So let's go back to KiCad and generate that. Now I'll just click on generate drill files. It seems like we have way too many options, but we can get rid of them by just selecting the latest Gerber format, Gerber X2. In this format, KiCad will choose the best settings to generate the drill files. So once that's done, we'll click on generate drill files. So even this is done. I'll close this. Now I'll open up the folder and see if our drill file is generated. Now here you can see we have generated two drill files. One is non-plated through hole and one more is plated through hole. So this plated through holes are for the pads and the non-plated through holes are for the holes that we make to fit in a case. With these steps, we have fully generated Gerber file, and this can be directly shared as a folder, but it's just more convenient to share it as a single zip file. Also, the most manufacturers and their online sites only accept zip file. So we can quickly do that. I'll just select the Gerber folder and compress it to zip file. Just to be sure, we can also verify whether the zip file have the correct information by using KiCad's Gerber viewer. We can open up the Gerber viewer by going to the KiCad's project window, and under this we can click on Gerber viewer. Here most of the tools and the navigation style is very similar to the ones from the schematic and the PCB editor. So it should be pretty easy to understand and use. Now let's see how we can bring up the zip file into this Gerber viewer. Go to File and click on Open Zip Archive File. And here you select your Gerber file and click on open. And here you can see the file has been successfully loaded, and also you can see all the layers that we designed during our PCB development. Now we can use these tools and compare this Gerber file with the design file that we have made. KiCad provides plenty of options here in Gerber Viewer. It's pretty good to use, but it might not be necessary all the time. So there are some online tools which can give you some beautiful SVG files when we feed in this Gerber file. We can do that by going to pcbcupid.com/tools/Gerber Viewer. Here you can just upload the zip file and you can see we have the output as a beautiful 2D image. And you can also go to Layers tab and use these interactive menus to analyze the Gerber files that were generated. We can also use this button to download the SVG file directly to your local machine, which we can later showcase on a website or can be converted into other image formats to share on social media. You might think we are done with the PCB and we can just send this to manufacturing. Well, sorry. I will definitely not send this PCB for manufacturing. Even though it meets the standard and it's good looking, it needs to be further optimized for production, where this can be easily produced for hundreds if not thousands at very minimal cost while efficiently manufacturing. Luckily for this circuit, we got all the symbols and everything looks darn good. But there are situations we might not have the proper symbols for the components. For example, if I search for the ESP32 module on the schematic editor, I can see some ESP32s, but these are just the metal cap ICs and not the modules as a whole that is used for prototyping. In this case, we might have to create a custom symbol or we can search for the symbol online, because there is always a high probability that someone might have either already requested for a similar symbol or they would have made a custom symbol and published it online. I would always prefer to make a custom symbol because it will reduce the unknown variables that are introduced to the circuit. But once you find a reliable source to get your symbol and footprints, it will reduce a ton of work down the road. Fortunately or unfortunately for this particular circuit, we might not need to create custom symbols. So we'll try to recreate one of the existing symbols to learn how to use the symbol editor and learn how to make custom symbols. We'll try to do this ATTinyIC symbol while following the library convention provided by KiCad. I'll be heavily relying on these guidelines to build the symbols even though it's not a requirement, because following this process will make it a lot easier to maintain a large amount of custom libraries, which we'll discuss further in the future videos. Now to start, we can either use the icon on the toolbar or we can just go to KiCad's project page and click on the symbol editor. Here in the symbol editor, the navigation is pretty simple. We have the scroll to zoom in and zoom out and middle click and drag to pan. Not just the navigation, most of the tools are also very familiar to what we saw in the schematic editor. On the left, we have the list of libraries arranged in alphabetical order which already exist within KiCad. We can create a custom symbol and store it within any of these libraries, or we can modify an existing symbol. But let's try not to mess the default libraries and symbols. Instead, let's start with creating a new custom library. To do that, go to File, click on New Library. In this pop-up, we can either select whether this library should be available on every single project that we are going to make, or we just need this library to be on this particular project. This really depends on how often you're planning to use the custom components. If you just need it for this project, select the project option. But if you need these symbols on other projects as well, select Global. After the selection, click on OK. Now KiCad will ask the location where you want to save the library. If it's related to the project, I would suggest to save it in the same location as your project file. If not, create a folder in the desired location just for KiCad libraries and store under it. While naming, just don't name the library as My Library or Custom Library. It can get really confusing once we start to make more of these. So try to give some thoughtful names, or the better option would be to follow the library convention provided by KiCad, according to which I'll name this library as MCU_microchip_ATTiny85. Then click on Save. You can see we have the custom created library here. I have to slightly modify the name so that it does not conflict with the already existing libraries. Since we have the library setup, we can create the custom symbol under this library. Make sure the library is selected and click on Create New Symbol. This will create a pop-up where we can enter the symbol details, starting with the symbol name. If you check the KiCad's library convention, it will recommend us to use the manufacturer's part number. So I'll do the same. I'll just type 80tiny 85-20mu. Next, select one unit. That's because KiCad lets us create multiple units for the same symbol. For example, let's say if I want to create a symbol for Arduino, I can break down the full module into 3 parts, where I can group the analog pins, digital pins, and power pins as 3 different units. But this is a pretty simple circuit, so we'll just stick on to one. And I would suggest keeping rest of the settings to default. If you'd like to know more about these features, you can read more about them on the KiCad's library convention document page. Here we can see KiCad created the symbol with only the designator, the letter U. First, let's set up the grid settings. In the previous videos, I did not explain much about the grid sizes. But to make a good custom library, try to keep the grid value to 1.27 or 50 mils, because as per KiCad's standard library convention, all the pins should be 50 mils apart. By setting the grids to these values will make our jobs a lot easier when arranging the pins around the symbol. Now with this grid setting, first let's start with creating an outline for our symbol. I'll use this rectangle tool and create the outline. Then use the keyboard shortcut E to edit the rectangle and click on Fill with Body Background Color and then click on OK. Currently the dimension is a little random, but we can always adjust that later when we do more customization. Anyway, now let's add a few pins to this symbol using the Add Pin tool. And for now, forget all the settings. I'll just give the pin number as 1 and then click on OK. By the way, it's the same shortcut to rotate the letter R and to move letter M. And once you're satisfied with the position, just do a left click. Now we'll try to follow the convention while adding the pins to the symbol, where the power pins are at the top, the ground at the bottom, input or control pins on the left, output and driver pins on the right, and finally arrange all the GPIO pins or the ports in the numerical order. If we follow the rules for this symbol, we'll have one pin on the top, one pin on the bottom, and the rest on the right of the symbol. Currently, all the pins have the same name and same property. To change this, you can either select the pin and do a right click and then click on Properties, or you can use the shortcut letter E. Here, we'll start with the pin name. I'll name this VCC, and according to the data sheet, this pin corresponds to pin number 8 on the physical IC. Now for the electrical type, power input, then graphical style to default. Again, if you like to know more about the rest of the settings, you can always refer to the library convention document. But for now, I'll leave everything to default and then just click on OK. So we can follow the same process to do this for each and every pin. Once the pin setup is done, we'll use this anchor tool to make the origin to the center of the symbol. Now our symbol is ready. We can either save it by using the Ctrl S command, or we can just click on this icon over here, which will save the file automatically and also will add it to our current project. We can quickly check that by going to the schematic editor. Click on Preference and then click on Manage Symbol Libraries. Since we opted this library to be only on this project, click on Project Specific Library. And here we can see we have the library that we made. If you like to include this in every single project, we can do that by going to Global Libraries and adding it over here. Since we are anyway in the Library Manager, I'll also show you how we can add external libraries to KiCad. There are a lot of good places to search for open source symbols, but I would recommend using SnapEDA or Octopart. They have pretty good UI and it's pretty easy to search for the part that you're looking for. And also support multiple design platforms other than KiCad. For now, let me just show you how we can add from SnapEDA. Just go to snapeda.com and search for the part that we need. In this case, let's try searching for the part name 80tiny85. Once you find the part, just click on download both symbol and footprint. Here you can see we have multiple options. Since we are working with KiCad, just select KiCad. Then click on version 6 and later. Once the file is downloaded, we can uncompress the file to get the symbol and the footprint. Now to add this to KiCad, go to KiCad Library Manager. As an example, I'll show you how to add this external library to your global library so you can use in every single project. Click on this folder icon, then select the symbol file that we just downloaded, which will have the extension KiCad_SYM. Then click on open. This will add the folder to the global library. Now we can confirm this by going back to the schematic editor. Now if I search for 80tiny85, we have two new options. That is one from the SnapEDA, that is 80tiny85-20pu, and another one that's custom created by us, that is 80tiny85-20mu. You can see we have both the custom libraries, the one we created and the other from the SnapEDA. And this is how you make custom symbol for your schematics. In our PCB, there are quite a few things that needs to be optimized. Look at the cell holder, for example. The 3D model is way smaller than the actual footprint. That's because we used a different size cell holder as an alternative instead of using the actual footprint. Because KiCad cannot hold all the footprints that's available on the market. Now let's try to fix this by making our own custom footprint. We can't just dive into the footprint editor just like how we did with the symbol editor. To make a custom footprint, we need to have proper details about the components like the shape and its dimension, because the footprints will reflect the physical component. Luckily, I could find the datasheet for the cell holder I have, which has very precise measurements. With these values, we can jump into the footprint editor to create the footprint for the cell holder. Just like how we open the symbol editor, we can do the same for the footprint editor. You can either click on the footprint editor icon from the PCB editor, or you can directly access it from the KiCad's project window. This footprint editor has tools and navigations that are very similar to the KiCad PCB editor, except we have all the footprints that are available on KiCad arranged here alphabetically. To start, we'll create a new library just like how we did for the custom symbols, so this way we don't mess up the default ones. Go to File, click on New Library. And I want this footprint to be available only on this particular project, so I'll select the project option and then click on OK. Now while naming, I'll try to use KiCad's naming convention. So the name of the library will be something like cellholder_txt. This is not mandatory, but trust me, it will help a lot while managing a huge amount of custom libraries. For now, I'll just click on Save. And then we'll select the created library. And then click on Create New Library using this icon. And I'll name the footprint as cellholder CR2032. And make sure the footprint type is through hole. And then click on OK. With this, we have the library set up. Make sure you change the grid size to 10 mils to make the drawing more precise. Now with these settings, let's try to draw a shape of the PCB with proper dimension from the datasheet. Now I'll just move these values aside and make sure the front silk layer is selected and select the circle tool. And I'll draw the circle slightly larger than the diameter we need. So I'll make the radius slightly larger than that's required. This will make sure the silk layer is visible even after we solder the components. Once that's done, we'll go to the circle properties and change the thickness to 0.15, which is recommended by the KiCad's convention. Then click on OK. Next, let's add some paths so we can place the components on the footprint and solder them. For this, we can use the path tool. And then click on the places where we need the paths to appear. And always remember, the path one should be on the left side of the footprint. KiCad uses the pin information to associate the schematic symbol with the footprint during footprint assignment. So make sure the pad numbers and the pin numbers match each other. For example, if the battery symbol have positive on the pin 1 and negative on the pin 2, the footprint should have positive on pad 1 and negative on pad 2. We need to be very careful at this stage so this doesn't mess up our entire circuit. Currently I place the pass just eyeballing it, but we need to make sure it's very accurate. So I'll use the data sheet along with I'll use the measure tool and the dimension tool to make the placement of the patch very precise. Now with that done, I'll try to make the shape very similar to the component. So first let's add the excess part over here. We can easily do that by using the line tool. This circle can be a little annoying because we can't get rid of this excess part. And KiCad also does not provide a trim tool where we can just delete this particular section. Instead, we can use the arc tool to recreate this curve. So I'll use the arc tool. I'll select the origin. I'll select the starting point. Then the ending point. Now we can delete the circle that's behind the arc. This footprint should be sufficient to be used on our PCB. But according to KiCad's convention, there are a few more steps that we need to follow. First, we need to make sure the shape of the pad 1 is rectangular. So click on the pad 1 and then go to properties by clicking the shortcut letter E. And here under pad shape, click on rectangular. While we are under the settings, you should also make sure under copper layers, all copper layers are selected and both front and back copper mask is selected. Then click on OK. These settings were not mandatory, but it will help us create a footprint with very minimal design error. Now there is only one last step remaining to complete the footprint. That is to add some courtyard to the footprint. We can do this by selecting the front courtyard and then using the arc tool again. We'll draw the curve with a clearance of 10 mils from the silk layer. Then I'll use line tool to finish the rest of the graphics. Now to verify that the footprint has been included into our PCB layout library, we can go to the PCB editor, click on Preference and then click on Manage Footprint Libraries. And under this, if you go under Project Specific Library, we can see the custom footprint that we created, that is cellholder_txt. Now let's see how this custom footprint will affect our PCB. I'll just click on OK. Let's select the cell holder footprint, then right click, then click on Change Footprint. And here make sure Change Selected Footprints is checked, and then under New Footprint Library ID, click on this icon and search for cellholder_txt. Then double click the cellholder CR2032. Finally, click on Change. You can see after few adjustments, we have successfully updated our custom footprint on the PCB. Alternatively, we can also search for components online and then replace the footprint. Especially if you're using sites like Mouser, you can easily find the footprints for the parts that you purchased. But if you shop somewhere else or buy it offline, you can always end up using third-party sites like SnapEDA or Octopart. Since we have already downloaded the part from the SnapEDA in the previous video, we'll just see how we can add that part here. I'll go to the Manage Footprint Libraries again, and under this, I'll click on this folder icon. And here I'll navigate to the folder and select the folder where we have the KiCad_mod file. In this example, I'm using 80tiny85 because that's what we downloaded in the previous video. Now let's try changing the 80tiny85 on our PCB with the ones that we downloaded from SnapEDA and see how that affects our PCB. It's not that bad, but I preferred the previous footprint. Here you can see I tried to make a PCB with the actual dimension, and there are a lot of issues with the placement of the components, mostly due to the through-hole components we chose. So let's try to remake a new version for this PCB. Unfortunately, KiCad currently doesn't support version control by default. We have to either use a git or we have to duplicate the KiCad project folder to make a new version. In this video, I'll use the latter method so it would be easier for people who are unaware of how git works. I'll just duplicate the project folder and open the PCB layout of the project. Currently, we'll keep the existing layout for the reference and see how we can fit all these components within the required dimension. And to get this dimension, let's take a look at the 3D model and check for the dimension of the base where the PCB will be sitting on. You can check the link in the description where you can download this 3D file and explore for yourself. In this case, we need 18 mm in radius. But making a PCB with the exact radius of 18 mm can cause tolerance issues while 3D printing this model. So let's go back to the PCB editor and make a circle with a radius of 17 mm in the edge cut layer. This will give us a little wiggle room for the PCB to fit within the model without any tolerance issues. Before starting to place the components onto the shape, go to the board setup and enable FFab and BFab. We deactivated these layers to reduce the complexity when we started learning KiCad. But now we'll use this layer to do some reference drawings which will help us align the footprints on the PCB. Now with the FFab selected, draw lines across the circle both horizontally and vertically. We can use these lines as guidelines to align the footprints and maintain the symmetry of the PCB. This is not required, but this will make sure your PCB is aesthetically more pleasing. Now let's start with the largest footprint that we have on the circuit. So that will be the cell holder footprint. To place it very accurately within the PCB, you can just play around with this grid settings to make sure that you efficiently use the spacing around the PCB. Once we have aligned the cell holder to the lines, you would have realized this footprint alone consumes 70% of the PCB. But still, I don't want to change this footprint even though there are other alternatives which can take way less space, either by using a different cell or by using a different cell holder. For example, if I search for the term minimum footprint cell holder CR2032 online, I can find plenty of different options. But the issue is most of them are very expensive and not easy to source at very low quantity. So here I'm trading off the space for easier sourcing and cost reduction. Coming back to the PCB editor, we'll try to move the LDR, LED and the microphone to the PCB. Since all these components are extended and not going to sit on the PCB, we don't need to have any of these fancy silk layers. We can easily replace them with the same footprint as the microphone and arrange them in order so it's easy to assemble within the 3D model. I know I'm overlapping the courtyards because I have to break this rule to fit the components within the PCB. But at the same time, I'm also aware this won't compromise the functionality of the PCB. It just adds a little bit of hassle during assembly, which I can probably manage. Now to store all these footprints in a compact way, I can remove all the graphics around this footprint. Can do that by going to the Properties, Edit Footprint, and we'll select these and just hit Delete. And here you can see saving this will only apply changes to the current PCB and it won't affect if you're starting a new project. So that's a pretty good option that we have. But if you want to use this for multiple projects, you can always choose Save As, create a new library and then store within it. For now, I'll just click on Ctrl S for save and let's go back. And you can see we don't have the silk layer for this. Similarly, I'll do for the rest of the two. Next, we'll get the 80Tiny85. It seems like there is no way we can place the 80Tiny85 on the top layer of the PCB. We can try placing this footprint to the bottom of the PCB by flipping the footprint. We can do that in two ways, either by using the shortcut letter F or you can just right click and click on Change Side. But still this would cause a lot of issues during soldering and how it might interact with the cell holder. So how about we change the 80Tiny85 to the SMD version? Let's quickly check on the 80Tiny85 datasheet. Here we have the dimension and the footprint for the SMD version of the 80Tiny85. But the big question is, can I source them? After a quick search online, I finally found the part. It seems like it's slightly a higher price when compared to the through-hole counterpart. But this version of 8085 will be a better candidate for our PCB. So let's go back to the PCB layout editor and change the footprint of the 8085. From the previous videos, you should be familiar with how this process works. Luckily, we did not have to create or download an external footprint for this 8085 SMD, as KiCad had them by default under the SOIC package. Just to be sure, I'll double check if the footprint dimensions are matching with the dimensions on the datasheet. That looks pretty good. We'll place this footprint under the cell holder. At this point, I want you to remember assembling components on both the side of the PCB can be cumbersome. But it's still doable if you are doing it for a small quantity and you are doing it by yourself. However, during large production, it can increase the cost significantly along with the complexity of the PCB. Therefore, opt for two-sided assembly only if it's necessary, or stick with one-sided assembly. In this case, I'll convert most of the components to SMD and place all of them on the bottom side of the PCB. So I can perform automatic assembly on the bottom, and once the assembled PCB arrives, I can just install the cell holder manually with very little soldering. Let's start with changing the footprints of the through-hole resistor into the footprint of SMD resistors. For many beginners, these names might be very confusing with the package names and the various codes. So choosing the right package for the SMD resistor will depend on multiple factors. First, power rating. This will depend on the voltage and the current consumption of the circuit. In our case, it's pretty low. The voltage is around 3.3 volt and I'll assume the circuit consumes around 50 milliamp. With this value, we'll roughly get the power of 0.165. This is just an assumption and I'm exaggerating the values. But in reality, the circuit can even consume lower power with proper optimization. According to this value, if we try to select, we have the options from 2512 till 0805. Maybe even 0603 or 0402 depending on the manufacturer. Since now we know the range of package options we have based on the power rating, we need to shortlist these values based on the size constraint in the PCB, ease of assembly, and finally the cost. In terms of size constraint, we have plenty of space on the PCB, and also we need to place only 3 resistors. So still our option lies between 2512 to 0402. Since I'm not planning to go for mass manufacturing, I want to assemble most of them by myself. The 0402 package and 0603 package makes the assembly job a little difficult because the size of these packages is roughly around 1 mm. And without proper tools, assembling these small packages can be quite hectic. Anyway, with this, the options fall between 2512 to 0805. Now it's really your choice what you need to select. Personally, if I look into the availability and the cost, I already have plenty of 0805 packages, and also it's extremely cheap for me to source them at very small quantities. Whereas for the other packages, I might have to buy them at a larger quantity and invest again. So I'll stick with 0805. But remember, you're totally free to choose based on your requirements and the availability. Now coming back to the PCB layout, I'll change the resistors footprint with 0805 package. And here, KiCad provides me with 2 options. One without the hand solder tag and one with the hand solder tag. I'll choose the second one because this will slightly have a larger pad for easy soldering with a soldering iron. So I'll quickly do the same for the rest of the resistors. We need to make sure all the SMD components are on the bottom side of the PCB. So we'll make sure to put all these SMD components to the bottom layer by pressing the shortcut F. So now it's much easier to place the resistors on the bottom layer of the PCB. Similarly, the switch I chose is quite large, and soldering on the top layer will just increase the cost of assembly, just like I said before. So I chose an alternative footprint for which I already have the component in hand. But accessing this from the bottom can be a hassle when the PCB is placed on the model. So I'll cut a small slot using the edge cut layer and these graphic tools. This will give me access later where I can turn on and turn off the switch without actually turning over the PCB. With this, we have successfully compressed the size of the PCB significantly from 36 mm to just 17 mm. And this will perfectly fit within the 3D model. For the rest of the design, you just have to follow from the video number 10 till number 13, which goes through the process of routing, DRC check, and creating custom graphics. So I'll just delete this PCB and do that in a very quick way. Now I can generate a Gerber file for this PCB and send it for manufacturing. And thanks for watching the series until the end. We have covered a wide range of topics related to KiCad 7. And I really hope you learned valuable skills and techniques for designing effective and efficient PCBs. If you have been following this series from the start and you have been working on something new, post your first PCB for review on PCBCUPID and get feedbacks from other users. If you find this series helpful, subscribe to the channel for similar content and also share it with people who might be interested in learning about PCB. And also, if you like us to make a tutorial or a video on a particular topic related to PCB, feel free to comment them below. Until then, keep learning and keep creating.